All right, today we're going to look at section 7.4. That's integration of rational functions by partial fraction, right? Remember, the definition of a rational function is defined as some function p over q, where both p and q are polynomials, all right? So why do we need to know this technique? Let me get my annotation. All right, so first thing is, if I have to integrate something that looks like this is a rational function. Clearly, it's a little tough for us because this doesn't look like a U sub. It's not a trig substitution. So the next thing that comes to mind is to try and use partial fraction. And the idea here is, if I can split this into two functions, you see the idea is I find two functions that when combined gives me the same result, then it will be easier to integrate such functions. So for example, if you integrate in this side, it will be much easier than trying to integrate this, all right? And because we know the integral of each of these p's, so that's the whole idea. We're trying to move from something in this form all the way to two functions that we can actually integrate. That's what partial fraction does, all right? So let's go through the first case. The first case is the degree of the numerator is greater than the degree of the denominator, all right? I'm going to expand this by saying that not only greater than, it includes greater than or equal to. So let me just add here, greater or equal. All right. So take note of that. I know in the textbook, they just mentioned greater than, but I'm telling you now that you consider this method when it's greater than or equal to. So your first step has to be long division. So once I give you the integral of the rational function and you discover that the polynomial at the numerator has a greater power or has the same power as the polynomial of the denominator, your first step is long division, all right? And when you apply long division, you're going to end up with something that looks like this. So we call this the dividend. So that's a dividend. We call it the dividend. All right. This one near the bottom, we call it the divisor. And then this PC is a quotient. So it's the result that you get from the division. So everything that goes on top of your long division there. And then the R there just stands for remainder. So whenever you do long division, this is how you want to write it. You want to say quotient plus remainder over some divisor, all right? Let's go through this example. So let's look at example one quickly. So for example one, you can see that the degree of the polynomial is 3. The degree of the polynomial at the bottom, there's 1. Therefore, I need to start with long division. What did I mention? I say if the degree of the numerator is greater than or equal to that of the denominator, to start with long division. All right, this is how we do long division. You have x cubed plus, remember there's no x squared, look there at the top, so that's why I just put 0x squared. There's an x and there's no constant, just put 0. So I just write it in this form to make things easy. And my divisor, there's x minus 1. Let's see how it works. So you use the first, so you say x cubed divided by x. Or you say, what do I multiply x by to get x cubed? Obviously, it's x squared, all right? That's why we have x squared there at the top. What do you do with the x squared? You multiply all of this by the x squared, what you have there at the top. So you have x squared times x, that's how we got x cubed. X squared times minus 1, you have minus x squared, and then you subtract. Take note, you subtracting, that's why I put a little subtraction there. X cubed minus x cubed, obviously there's 0x cubed, so it falls off. And then take note of this minus, there's a minus here and we subtract it. So it becomes 0 minus minus, become positive x squared. Most of you make this mistake. You just ignore that you subtracting and you just say 0 minus x squared and they end up with a negative here, which is wrong. So when you subtract, you need to say 0 minus, you consider the sign here as well. So 0 minus minus, right? Then the next thing is you need to bring down these terms here. So you bring down x, and I'll just bring down 0 as well. Again, you use the first term, the x squared, you divide by the first term of your divisor. X squared divided by x, I get just x. That's why we have x there at the top. Again, you use this x at the top, you multiply by everything in the divisor, so you get x times x is x squared. X times minus 1 is minus x. Again, you see I'm putting a little subtraction there to show that I'm subtracting. X squared minus x squared, you see, falls off. X minus minus, take note, is 2x. All right. And the obvious is 0 minus 0, which is 0. All right. Then we go again. We don't stop there. All right. We take 2x divided by x. It just gives you a constant of 2. There's a 2 there. You take the 2, you multiply by the divisor, you get 2 times x is 2x. 2 times minus 1 is minus 2. Again, we're subtracting as usual. 2x minus 2x falls off. 0 minus minus become positive 2. Now this is where you stop. Why? Because I have a constant, and so I have x to the power of 0. You see, there's no x here. It just means x to the power of 0. It's 2 times x to the power of 0. And here I have x to the power of 1. The fact that I can take 2 and divide by x, I know I have to stop there, right? And you need to write it in this standard, this form here. So you're going to have this whole, so this Sx, which stands for the quotient, represents everything that you see on top here. And you're going to say plus the remainder, which is 2 in this case, over the divisor, which is x minus 1. All right, this is what I did here. So Sx is this. So this is this, and then this Rx over Qx is this. You must write it in this form before you start integrating. Once you have it in that form, the integral of this rational function simply becomes the integral of everything here on the right-hand side. Obviously, this is just a polynomial, straightforward. You just apply the power rule of integration, x cubed over 3, x squared over 2. Integral of 2 is just 2x. Now, what's the integral of 2 over x minus 1? You know you're going to have 2 times ln absolute value, all right? So this is a linear function, so you end up with ln absolute value. And then please adjust it to the plus c there, right? There's no space there, but it's a plus c. So this is the very simple example where we looked at the case where the degree of the polynomial, the numerator, is greater than or equal to that of the degree of the denominator, right? When we talk of degree, we're just talking of the highest power of x in that polynomial, all right? Let's look at the next example. Now we have a case where the degree of the numerator is less than that of the denominator, all right? We say we need to calculate the values of constant depending on the factors. And in this case, factors are not repeated. So take note, this is a special case where factors are not repeated. So first you observe is degree at the top is smaller than that of the bottom. That's where we start looking at partial fractions. How does it work? You factorize this bottom piece, take note x is common. That's why I took out an x in the beginning. And then I tried to factorize this quadratic function, which everyone knows how to do that. You just get x times 2x minus 1, x plus 1. Now, how do you expand this? Take note, these are all linear functions. For linear function, you assign single letters or constants, all right? So for x, I assign it an a, so a over x. For the second factor, the 2x minus 1, I have b over 2x minus 1. For this third one, there I just have c over x plus 2. After writing this piece here that you see in bracket, what do you do next? All right, we need to solve for this constant. We multiply both sides. So we multiply this left-hand side with this right-hand side. We multiply both sides by the product of all of these factors. So this piece here is here at the bottom. You see that's what I'm doing here.
Oh,
right?
okay.
Multiply both sides by those factors there at the bottom. And notice see the left-hand side, this factor there will simply cancel with this, all right? You're left with just this polynomial that was there at the top. On the right-hand side, now let's see what happens. I will take you through step by step. If you take a over x, so we're looking at this first one, a over x. If you take a over x, you multiply by the whole of this. Take note that x will cancel with this, and then you'll be left with a times this remaining two factors. That's how we got this result here.
So, siya taking mo ko ya tahan.
Please, can
Kaya
you
kung
mute?
wala ko
Can you mute yourself?
ka-BIOS, I have to figure out which pattern opens BIOS so that I can boot from the USB.
Can't you
Only
do it at
Windows.
home because though it was always trying to the movie.
All right, I'll just mute them so that we can proceed. Please, when you join the class, just mute your mic. We're not interested in what you're saying at home, all right? Unless I give you the right to speak, then you unmute yourself and you talk, all right? So let's look at the second one, b over 2x minus 1. If you multiply it by the product of these three factors, the 2x minus 1 here at the bottom will cancel with this piece here, and you'll be left with b times x plus 2, which is why we got that. Obviously, following the same idea, you get this. All right. Now, there are two ways of solving this. The method you see here is just one of the methods. What I did was I just multiplied this bracket out. So I multiply this, multiply this, multiply this. All right. And I compare the terms on the left and the right. I see the coefficient of x squared here is 1. The coefficient of x squared here, notice it is a 2 times a. That's how we have 2a there. The coefficient of x squared here is 1. So 1 times b, you see there's b. The coefficient of x squared is 2, and this is c also says 2c. That's how I got my first equation. Then I compare the coefficient of the linear term, which is x, is 2. That's a 2 there. I look this side is 3 times a. This side is 2 times b. And then here is minus 1, which is just minus c. All right. And lastly, you compare the constant term, which is minus 1. This side, you have minus 2 times a. This one has no constant term, no constant term here, no constant term here. So you just have minus 1 equals to minus 2a. And from there, you can solve for a. And if you solve for a, obviously, you substitute the previous two equations. There you end up with two equations, two unknowns, which you guys know how to solve that. That's just substitution. All right. Now, what happens after you solve for A, B, and C? Just before I do that, I'll explain another method, which usually is the most popular method, is if you have linear factors, if you equate them to 0, notice you get x equals to 0, that will come from this. X equals to half will come from this. X equals to minus 2 will come from this other factor. So you say let x equals to 0. Notice if you let x to be 0, this whole term here, if you substitute 0 in the place of x, this whole term falls off. This whole term here falls off because you see there's an x there, there's an x there. You just left with the substitution of 0 in there, and on the left hand side, it's easy to solve for a. If you let x to be half, the same thing will happen. This whole piece here will fall off. This whole piece here will fall off. You'll be left with just this one to solve. So you can use that method as well, all right? Or you can expand and compare the coefficients. So use a method that works best for you. All right. Once you've solved for the constants, so in this case, you have a is half, b is 1 over 5, c equals minus 1 over 10. All you need to do now is you put it back. So just get my annotation again. So where I see a, I just put the half. Where I see b, I put this. You see, I'm just writing the constant there, and I have to integrate this result. The integral of 1 over x is just lean absolute value. Always try and take the constant in front of the integral to make your life easy. Now, this is where most of you get stuck, all right? This is a linear term. Yes, you're going to get lean absolute value of this linear function. But be careful because the coefficient of x here is 2. Or if you can't see how we got this half, please use a U substitution there, all right? You will see where the half is coming from. The idea is when you integrate and you have a linear term, you need to take 1 over that coefficient of x there. Where's why you see we have 1 over 2 there. All right, then lean up the whole function there. This is also a linear function. Obviously, it's just lean absolute value and the coefficient is 1. So there's no need to do a use of that. And notice here, I try to simplify as much as possible because I have 1 over 10 here and I have 1 over 10 here. If I take out 1 over 10, I have lean of a function minus lean of another function. It's just lean over the first function divided by the second function. All right. You see, I'm applying some properties of logarithm there. If this constant were different, then I'll stop there. All right. I'll just say plus c. So guys, be careful with that when you simplify. All right. So let's see if the next example gets any easier. All right, let's look at this one. This is a nice one. Example 3, let's look at it quickly. So there you have difference of squares. I tell you that a cannot be 0. It's true, because if a is 0, you trying to divide by 0, which means that integer is invalid, it's undefined. That's why a cannot be 0, all right? And this is difference of 2 squared. It means you can write it as x plus a, x minus a. Remember, these are linear factors, means that you're going to assign just single constant for those. So it's just a constant, a over x plus a, b over x minus a. And then just do the same technique. So for a and b, you just get b is 1 over 2a, and capital A just minus 1 over 2a. All right. And obviously, keep in mind that this small a is a number, it's a constant, because the variable here is x. You treat this a as just a number. It can be any real number, all right? So where you see minus 1 over a and 1 over 2a, just take them in front of the integral, because a is a constant. Take the constant in front of the integral, integrate, and then apply the rules of logarithm. Then you're good to go. All right. Is there any question from your side? All right, no question. I assume that everyone is happy. All right, someone said no. Now, this is where things get a little bit interesting. We have factors that are repeated, all right? Factors are repeated, all right? How do we do this? Let me just answer this question quickly. They say, so for the partial fraction, will you always have a linear absolute value in the answer? The answer is, it depends if you have linear factors. If you have linear factors, you always have linear absolute value. But now we're going to see a situation where you won't necessarily have only linear factors, so you have something different from linear absolute value. All right. So linear absolute value arises because we had linear factors in the partial fraction expansion. All right.